All right, so mechanical physiology of the heart and the cardiac cycle, that 0.8 seconds, everything that happens within that lub duct, is what we're going to start talking about. So all of the events associated with one heartbeat is considered our cardiac cycle. So each heartbeat represents one cardiac cycle, which consists of atrial and ventricular contraction and relaxation. But for the rest of the PowerPoint, I'm not going to use the terms contraction and relaxation. The word for heart contraction is systole. It looks like it's systole, but it's pronounced systole. And the word for relaxation is diastole. So we can say one cardiac cycle consists of both atrial and ventricular systole and atrial and ventricular diastole. And that creates the sound lub duct. So mechanical physiology is the actual process where blood fills the chambers and pumps them out. So cardiac muscle cells contract to produce coordinate contraction, where your atria kind of have a spiral pattern and they ring out and push blood down into the ventricles. Then the atrioventricular valves, the tricuspid and bicuspid, close. As blood pushes back on the tricuspid and bicuspid, it makes the first loud heart sound. We call it the lub, or sound 1, S1. And then your ventricles contract and they push blood out into the pulmonary trunk and aorta. And then as blood comes back and hits the closed pulmonary semilunar and aortic semilunar valve, it makes the second heart sound, S2, the duct, the lub duct. Now, what we have to get used to seeing is that blood flows through those valves based on pressure changes. And this is a little bit like diffusion. This is the hardest thing of muscle physiology to understand. But blood is going to flow from an area where it's in high pressure to an area where it's in low pressure. And I'm going to give you some examples in a minute, with valves preventing backflow. So for instance, when the atria contract and blood is flowing from atria to ventricles because blood is a higher pressure in the atria at that time than the ventricles. And then the valves close between the atria and ventricles, because as soon as that happens, the pressure in the atria is then lower than the pressure in the ventricles. So the blood's going to want to go back. But we have those valves to make it go one way. So the theme of this next slide, as I go through these questions, are going to be that blood flows from an area of high concentration to where an area, or I'm sorry, not concentration, blood flows from an area where it's in higher pressure to an area where it's in lower pressure. All right, so I'm going to get to that in just a moment, but to understand those pressure things, let's look at our cardiac cycle. So we said that if we divide 75 beats per minute by 60 seconds, one cardiac cycle requires 0.8 seconds. And we will divide that into 4 phases: the filling phase, the contraction or isovolumetric contraction phase, the ejection phase, and the isovolumetric relaxation phase. So first, let's look at the filling phase. During your ventricular filling phase, this is the time period when the tricuspid on the right side of the heart and the bicuspid on the left side of the heart are open and blood is flowing from full atria down into relaxed ventricles. It happens for about 0.1 seconds. And first of all, what happens, those valves open before the atria contract and blood just kind of flows slowly into the ventricle. And then to get the rest of it out, the atria actually contract and push the remaining blood down into the ventricle. Now, at the end of the filling phase, we have end diastolic volume. That refers to what's happening in the ventricles. So what do we say the term diastole meant? Relaxation. So this is the end volume in a relaxed ventricle. Think about that. Would the end volume in a relaxed ventricle be full or empty? It would be full. So this is about the fullest that each ventricle ever gets, because they have to be full, and then when they contract, they're going to push blood out. So a full ventricle, the end diastolic volume, is about 130 milliliters per right ventricle and per left ventricle. So now we get into our contraction phase. So now we have full ventricles with end diastolic volumes of 130 milliliters per ventricle. What happens first are these atrioventricular valves, the bicuspid and tricuspid, close, because as soon as our ventricle gets full, our pressure is going to get higher in the ventricle than the atria, and we're going to have backflow of blood, so they close. But there is a very brief time period, as you can see in this figure, when the atrioventricular valves close, before the semilunar valves open. Remember that these valves open and close and blood flows from chamber to chamber due to pressure changes. Just because the ventricles are full does not mean that their pressure is not greater than the pressure in the pulmonary trunk and aorta. The only way this aortic semilunar valve and this pulmonary semilunar valve are going to open is if the pressure in the right and left ventricle exceed the pressure in the pulmonary trunk and aorta. So isovolumetric contraction is the phase where these ventricles are for brief milliseconds, closed chambers while the AV valves and SA valves are all closed, but your ventricles are contracting and generating tension so that they can overcome the pressure in these next two chambers, the aorta and pulmonary trunk. And whenever they generate enough tension and overcome that, then the pulmonary semilunar valve and aortic semilunar valve open and blood can be ejected into systemic and pulmonary circulation. Now, if we dissect the word isovolumetric, isovolumic means same volume, so it's contracting, but it's the same volume. We still have 130 in here, it's not going anywhere. And an isometric contraction you learned in the skeletal muscle lecture. So isometric contraction means that we're generating tension without actually shortening the muscle. So that's what's happening here. So the ventricular pressure is not yet high enough to push open the semilunar valves, so both sets of valves are closed and ventricular volume does not change. That is isovolumetric contraction. It is the shortest phase. Now finally, after we have generated enough contraction from isovolumetric contraction to overcome the pressure in the pulmonary trunk and aorta, your pulmonary semilunar valve opens on the right and your ventricle is contracted and pushes blood out into the pulmonary trunk to pulmonary circulation. And your aortic semilunar valve is opened on the left and your left ventricle contracts. Blood goes out through your aorta to get to systemic circulation. And that's the ejection phase, still pretty easy to understand. Now at the end of ventricular ejection, your ventricles now have what are known as end systolic volume. What did the term systole mean? Systole stood for contraction. The end of ventricular contraction, your ventricles should be fairly empty. But notice what happens. A normal end systolic volume, which is the volume remaining in each ventricle after they contract, after systole, is 60 milliliters. But what was a full ventricle? Remember, a full ventricle at end diastolic volume was 130. So if each ventricle had 130 milliliters in it, and after they contract, they have 60 milliliters in it, that means they only pumped out about 70 milliliters per ventricle, which is just slightly over half of the blood in each ventricle. That's interesting because that's not 100% efficient. There's always about half of the blood left in there. But the amount of blood ejected from each ventricle per beat is known as the stroke volume. So if you take a normal end diastolic volume, 130, and subtract a normal end systolic volume, 60, you would get a normal stroke volume as 70 milliliters. And that might be something you're expected to do on a test. Subtract end diastolic from end systolic volume, know how to do that to get your stroke volume. And again, the definition of stroke volume is the amount of blood ejected per ventricle each beat. And then finally, after your semilunar valves, your pulmonary semilunar and your aortic semilunar valve close, we're in our isovolumetric relaxation phase. And you should understand what isovolumetric means now. It means same volume, same tension, again, for a very brief period. Our ventricles are closed, but they have less blood in them. And this is going to be really brief because right after that, we're going to go back to our filling phase where the pressure in the atria overcomes the pressure in the ventricles and your tricuspid and bicuspid open and your ventricles begin filling again. All right, so here we see again, putting those phases with our EKG, our P wave is ventricular depolarization. After depolarization happens, we get our atrial systole. We begin ventricular repolarization. After that happens, we get ventricular systole.